All right, we're back. We're going to be on page 7 of notes 14 of Calc C, talking about logistic differential equation. This page, like the last page, just practice problems. So if you know what you're doing, plow ahead and just confirm. If you're looking to do the practice problems with me, follow along. Otherwise, use your time wisely in life, All right, so suppose that a particular population of bacteria obeys the logistic formula, blah, with P measured in milligrams and T in hours, find state L, K, and P of 0. All right. Well, this is not how I like to have it because this is not a 1. So I'm going to make that happen. P of T. 1,000. So I'm dividing everything that I see by 2. Now we're good to go. So L is definitely 1,000. So L is 1,000 milligrams. I don't know if I'm supposed to be using units on these, maybe. K is going to be 0.3. So since time is measured in hours, and when I plug in like 5 hours, it needs to multiply by negative 0.3 somethings to just give me a real number, not like it should have no units. So the units on this are per hour, which just looks so weird. And then P of 0, if I plug in 0, it's actually the easiest. It's easier to plug in 0 here. So let's do that. So we get 2,000 over 5. So 2,000 over 5 is 400. And 400 milligrams. So there's 400 milligrams of bacteria. I guess you measure bacteria in milligrams. I certainly did in these problems. All right, let's keep going. We got this. Suppose a particular population. It's like I forgot how to read there. I thought I was going to say particle because that's a really common calculus word. Like a particle moves according to bacteria. What's happening? Particle population of bacteria obeys the logistic formula, blah. What is, it's always when. Why's it got to be when? All right, let's see. Again, this is not the ideal form. So I'm going to divide everything by 3 halves or by 1.5. So by 3 halves. So what is 3,000 times 2/3 is 2,000. So dividing by 3 halves is the same as multiplying by 2/3, which is why I did that. And this will be 1. And then we have 7 halves divided by 3 halves is 7/3. I move my hand a lot when I'm adding and subtracting. It's like a physical thing for me for some reason. Okay, we got that. What is the population when it is growing the fastest? All right, so the limit as t approaches infinity of P of t is definitely 2,000. Therefore, population is 1,000 when growing fastest. I'm excited about that. Find when the population is growing the fastest. All right, so we kind of know how to do this. Like it's going to be the natural log of 7/3 over 0.2. It's going to be 5 times the natural log of 7/3. But I'm going to do the work because I think it's hard to remember that in the long run. So I need to know 1,000 equals 2,000. 1 plus 7/3 e to the negative 0.2t. So we cross multiply, we get 1 plus 7/3 e to the negative 0.2t equals 2. You subtract 1, you divide. So we're going to get e to the negative 0.2t equals, you subtract 1, you divide. So you get 1 over 7/3, which is 3/7. Now you're going to take the natural log. Negative 0.2t is the natural log of 3/7. Now I'm going to divide through by a negative, but the negative becomes the coefficient, right? So negative is the coefficient. Coefficients become exponents. So I'm going to end up with t equals the natural log of 7/3 over 0.2, which if we did it on the calculator would definitely say 5, the natural log of 7/3. Kind of like in general, I don't think this is worth memorizing. And if you're one of my students, you got to show the work, but you're going to always end up with t equals the natural log of a over k. It happens every time. And then sometimes it simplifies. but whatever. What is the maximum rate of growth for the population? All right, so this is actually, I like this question. Kind of catches you off guard because it's not the most common question that you're given. But this is saying to find dp dt, and then we know the time, but we also know the values. We want dp dt such that t equals, I guess, 1,000, which is pretty big. So I'm going to plug this into the differential equation that I never wrote. So actually, I'll move that over and find the differential equation, which we can do from here, right? We know L is 2,000. We know that K is 0.2, which is all that we need. So dp dt is K, so 0.2p, and then 1 minus p over 2,000. Didn't give myself enough room. That's the story of the notes. Didn't give enough room. All right, if we plug in 1,000, 1/5 of 1,000 is 200, not 20. And then 1/2. There's probably a thing here also, but I don't exactly know. Like, I don't want to. I mean, it's whatever. It's when you plug this in. I guess this is always going to reduce to 1/2. So it's half of k times p, like always when you do the maximum rate of growth, I suppose. I don't think that's worth knowing either. 1/2 of k. Oh, so this is 100. Interesting. What are the units on that? So it's population in milligrams and then time in hours, so milligrams per hour. All right. I hope I'm getting these right. I bet you do too if you're following along. I'm pretty sure that I am, but like, who could be positive? All right. Trick question. This is not how we like it. So redo it. dp dt. I'm going to take out the 2p, 1 minus. All right. So dividing by 2, well, factoring out 2 is the same as dividing by 2. So I have p over 5,000 over 2. So that's p over 10,000. 1, 2, 3. Okay, so the limit, no matter what the initial condition is, and this is like the thing that you gotta keep in mind. It doesn't matter what the initial condition is, the limit will be the same. This is frequently, when logistic differential equation is on the AP exam, this question is frequently a part of it. It doesn't matter what the initial condition is. This is the limit as t approaches infinity of p of t is gonna be 10,000. Whether you start above, so this is an increasing solution because you start out below the limit, right? Because 3,000 is less than 10,000. So it's an increasing solution, but it increases to 10,000. This, the limit as t approaches infinity of p of t is going to be 10,000. It's a decreasing solution. So like the question had been the range, right? The range of this solution is going to be 3,000, including 3,000, to 10,000, not including 10,000. So 3,000 you count, 10,000 you don't. The range of this one is going to be 10,000, which you don't count, to 11,000, which you do count. And the range is also, I think, a really good question. So you never, according to the mathematical model, get to the limit, which, you know, is kind of weird. So this is decreasing because 11,000 is greater than 10,000. All right. So that's a little bonus thinking about the range. Actually, I'll write down those ranges. So range, it's not really asking for it, but the range here would be 3,000 to 10,000. And the range here is going to be 10,000, not including 10,000, to 11,000, which obviously you can include because it is P of 0, like it better be in the range. So good questions, I think, across the board here. All right, I'm gonna be back in the next video. We're gonna do, the next 2 pages are review problems, like way back review, because you can never stop thinking about series. If you're not thinking about series, you're going to be in trouble in the long run. So these are good. They're going to be, I think, good. I don't know, but they're going to be about series based on the first question. So I'll see you in the next video.